Performance enhancement of permanent magnet DC motor with sepic converter through higher order sliding surface. ID number is 8811. The authors are R. Dhanashekhar, S. Ganesh Kumar and Marco Rivera. Abstract. In this research article, the authors proposed a new higher order sliding surface, that is proportional integral derivative sliding surface, to stabilize the rotating speed of the permanent magnet DC motor driven by DC-DC sepic converter. This controller offers numerous benefits which includes robustness, enhanced control performance, flexibility, implementation and low cost. The algorithm is developed for the load torques such as no load, constant, frictional and propeller types. Further, the features of the proportional integral derivative sliding surface are compared with the classical sliding surface, sliding mode control and a proportional integral controller by taking into consideration of peak overshoot, steady state error and settling time. Simulation and experimental results are obtained satisfactorily. Contributions: a proportional integral derivative sliding surface with a second order derivative and a second order classical sliding surface are developed and put into the effect of permanent magnet DC motor via a fourth order sepic converter. Restriction of order of the sliding surface is realized by investigating via relative degree and the order of the system. The behavior of the proposed PIDSS controller is analyzed in the presence of changing the reference signal and for various load torques such as constant load torque, fan type load torque, propeller load torque. Generalized procedure for designing the higher order sliding mode control. First, the selection of sliding surface, then compute the derivatives of sliding surface, find the equivalent signal from the higher order derivatives and also find the switching signal through the homogeneity approach, and finally the control law is based on the combination of continuous signal and discontinuous signal. Is the desired region is attained only the equivalent signal is continuous, if not both the continuous signal and discontinuous signal will be approached. Circuit description of sepic converter fed permanent magnet DC motor. The circuit consists of DC source, sepic converter and the permanent magnet DC motor as a load. The PWM signal for the sepic converter is generated from the higher order sliding mode control. 6 state equations are represented here. Simulation analysis. Table 1 represents the sepic converter and PMDC motor parameters. Table 2 represents the details of machine operation. For the selected speed profile in per unit and the selected torque profile in per unit, the speed responses for various speeds under constant load torque is represented here. For the same speed profile and load torque profile, the performance is shown here under frictional load torque conditions, fan torque conditions, propeller torque conditions. Table 4 represents the comparison of PIC, SMC, second order SMC with a classical sliding surface and a proportional integral derivative sliding surface. From the table, it is clear that the performance of PIDSS is better than the other controllers. This is the experimental setup which shows the hardware results for the sepic converter fed PMDC motor. Conclusion. Here the authors proposed a new higher order sliding mode control, that is PIDSS, and it is compared with a classical sliding surface, sliding mode control and a proportional integral controller. Simulation results done for PIDSS for various load torques and the experimental setup is under constant load torque condition. So from the simulation and experimental results, The proposed method is effective in both the estimation and the rejection of disturbances. Future scope. The proposed controller is extended for various higher order converters and loaded situations. This is the author's bibliography. Myself R. Dhanashekhar. Second author is Dr. S. Ganesh Kumar and third author is Dr. Marco Rivera. Thank you.